Hi everyone and welcome. If you're here, you're probably wrestling with problem 1.47 from Irodov's classic physics book. Well, you've come to the right place. We're going to break this thing down piece by piece. Okay, let's really dig into what this problem is asking. We've got a body spinning up, but here's the catch. Its angular acceleration, beta, isn't constant. It's actually getting bigger over time following the rule beta equals a times t. So what we're hunting for is the exact moment, the specific time t, when the total acceleration vector makes a perfect 60-degree angle with the velocity vector.
Now, before we even think about touching any numbers, we have to get our heads around the physics. What even is total acceleration for a point going in a circle? See, it's not just one thing. It's actually a vector made up of two totally different components working together.
First up, you've got tangential acceleration. You can think of this as the speeding up part. It acts right along the edge of the circle, always in the direction the point is moving. This is the one that's directly caused by that angular acceleration, beta.
And then there's its partner, the normal acceleration. You've probably heard it called centripetal acceleration. This guy is always, and I mean always, pointing straight towards the center of the circle. It isn't making the point go faster or slower, it's just constantly yanking on it, changing its direction, and forcing it to stay on that circular path. This is the turning part.
Okay, now this is where things get really interesting geometrically. The velocity is always tangent to the circle, right? Well, that means the tangential or speed up acceleration runs parallel to it, and the normal or turning acceleration is always at a perfect 90-degree angle pointing straight inwards.
So this brings us to the big question, right? We've got these two acceleration components, and they're acting at a right angle to each other. How in the world do they add up to give us that one total acceleration vector the problem is talking about?
And bam, here it is. This is the insight that cracks the whole thing wide open. Because they're perpendicular, these two components and the total acceleration vector form a perfect right-angled triangle. The total acceleration is just the hypotenuse. This is awesome news because it means we can whip out some simple trigonometry to relate everything together. All right, now that we've got a handle on the geometry, let's start building our plan. We're going to deconstruct this thing and assemble our physics toolkits.
So here's the game plan. First, we need to get the angular velocity, omega, from the angular acceleration, beta. Easy enough. Then we need to find expressions for our two acceleration components, the tangential and the normal. And finally, we'll use our trusty right triangle trig to connect those components to that 60-degree angle.
All right, we've got our toolkit ready. It's time to put it to work. The logic is all there. We just have to apply the physics, step by step.
Okay, so here's the plan laid out nice and simple. 1. Integrate beta to find omega. 2. Write down the formulas for the acceleration components. 3. Use trig to set up our equation with a 60-degree angle. And 4. Solve for time. Let's do it.
All right, first up, step 1, integration. We know that angular acceleration is just the derivative of angular velocity. So to go the other way, we just integrate. We take our function, beta equals at, and integrate it from the start, time 0, up to some time t. And that gives us our formula for angular velocity, omega, 1/2 at squared. Now for step 2, where we get our hands on the accelerations themselves. We just need to pull out our standard formulas from kinematics. Tangential acceleration is simply beta times the radius r, so that's atr. Normal acceleration is omega squared times r. We just found omega, so we plug that in, square it, and boom, we get 1/4 a squared t to the 4th times r. Perfect. Now, both components depend on time. Okay, this next part is absolutely crucial. This is where we connect all that physics math back to the geometry of the problem. Remember our right-angled triangle? The problem tells us the angle alpha is between the total acceleration and the velocity. And since the velocity points in the same direction as the tangential acceleration, alpha is just the angle in our triangle where the tangent is the opposite side, the normal acceleration, over the adjacent side, the tangential acceleration. And now for the really cool part. We take our expressions for the two accelerations and plug them into that tangent equation. And check this out. A bunch of stuff simplifies beautifully. But look, the radius, r, it just cancels out. Gone. This is a huge deal. It means the angle is exactly the same for every single point on this rotating body. Doesn't matter if it's right near the center or way out at the edge. And from here on out, it's just a little bit of algebra to clean things up. We just rearrange the equation to get t all by itself. We find that t is the cube root of 4 times the tangent of alpha
all divided by a. And that's it. We have our final formula.
And there we have it, our final equation. Now for the really satisfying part, let's plug in the actual numbers from the problem and get our answer.
So the problem gave us a as 2 times 10 to the minus 2, and of course alpha is 60 degrees. We know the tangent of 60 degrees is just the square root of 3. So yeah, we have everything we need right here.
Punch that all into a calculator, and what do you get? A nice, clean, beautiful answer. The time we're looking for is exactly 7 seconds. Okay, so we got an answer, 7 seconds. But what does that actually mean? In physics, just getting the number is only half the battle. The real goal is understanding the story it tells. So what's so special about 7 seconds? Well, think about it. The tangential acceleration just grows linearly with time, but the turning normal acceleration, that thing grows as time to the 4th power. It absolutely skyrockets. At first, the tangential part is bigger, but eventually the normal part catches up and overtakes it. At precisely the 7-second mark, the balance between these two components is just right to tilt that total acceleration vector to a perfect 60-degree angle, which leaves you with a really interesting question to chew on. How would any of this change if that angular acceleration was constant instead? That's a great one to think about for next time.